Thank you so much for inviting me today to this workshop. And well, it's nice to be here for many reasons. And one of these is also reminding me I became a scientist working in nonlinear optics, mostly inspired by Bugiato and Federico Casagrande. So it's that I think you are all familiar with. So it's really a pleasure now to contribute to this workshop. So I want to report on results from my research group. I mean, we work in ultrafast spectroscopy. And so what do we do? Well, basically we look at ultrafast dynamics in all kinds of materials, mostly I would say in molecular systems in the gas phase and in condensed matter. And in particular, what is ultrafast dynamics for us? It's really ultra short. I would say we are interested in really looking at the electron dynamics. So to be able to assess attosecond time scale, billionth of a billionth of a second. So the usual time in which electrons move in molecules and in which one can observe charge migration or charge injection in solids. And so in my talk, I would basically report on recent development in our attosecond technology, so in the XUV source that we use. And I will, explain why this is interesting and then go to the results. So we want to do spectroscopy with XUV and SoftX, and why? Well, because it allows you to have very high temporal resolution. If you go to the XUV, you can assess the attosecond regime because of the Fourier relation between frequency and timing, and this is the timing that you need if you want to assess electrodynamics. You can have a high spatial resolution for some experiments, and of course, there is also this very interesting aspect that you can get the chemical sensitivity. If you have photon energies that can really probe the edges in atoms, you can look at the role of an atom within a molecule. And this in ultrafast spectroscopy is quite interesting because you may assess the role of one atom in the full system, for particularly concerning, charge migration, for instance. So this is why we are interested in this spectral regime. And the kind of experiment that we do is pump probe experiment. So basically, we send pump pulse, which is usually it depends, but it could be mid-IR, visible, or infrared, to our sample, and then we probe it with XUV or SoftX probe. And then we measure signal that could be charge particles, or it could be radiation, depending on the experiment that we want to do. In the case that we measure the spectra, so we look at the transmitted spectrum from the sample in transit absorption spectroscopy. This is the scheme of the experiment, basically. So you pump in your system. This is solid, you drive some electrons from the valence beam to the conduction beam, and then there is some relaxation process, and you come with your XUV pulse and you look at the transmission through the sample, which basically you trigger some core orbital excitation and you look at how the spectrum changes. So now, what do you need? Which kind of source you need as a probe for this kind of experiment? Well, the ideal probe should have broadband coverage, for chemical sensitivity, and of course also for the temporal resolution, because you want to have extreme temporal resolution. One wants to have polarization control of the source, and of course high brightness, because in this kind of experiment, signal to noise is always a struggle, and so these are the characteristics. And how one can get this kind of source? There are different approaches. Of course, one can go to the free electron laser, large-scale facilities in which one can have access to very short pulses and very intense in the SoftX and XUV. But one can also use tabletop sources, and this is what I will show you today, the tabletop sources that we develop for doing this kind of experiment and the setup that we have available. So Tabletop sources are based on nonlinear optics, in particular on the high-order harmonic generation process. I assume you're not all of you familiar with that, so I will just give you a little hint on how it works. It's very well understood in the framework of the simple man model, three-step model. Basically, what you have is that you focus a femtosecond laser intense short pulse on a sample, which is usually an atom. And what happens is that you can have tunnel ionization in your sample. And then the free electron is driven by the external electric field. And it can get back and it can recombine with the parent ion. And this gives rise to emission of X-to-V light, as in a brane slalom process, basically. It's very similar to brane slalom. This process is characterized by a very low conversion efficiency of the order of 10 to the minus 6, 10 to the minus 9. And also it depends on the driving wavelength. And I'll get back to this detail later. But how does this radiation that you can generate with high order harmonics in your lab look like? So this is basically like how a spectrum look like. Is a spectrum composed of high order harmonics indeed, and why? Because the process is repeated periodically, every half cycle of the driving field. It really depends on the shape of the electric field and is repeated periodically. So you get those hot harmonics of your basically of your driving frequency. And in the temporal domain, correspond to a train of attoseconds pulse intrinsically. So I mean, it's complex setup, but stable top. And if you have a laser which is short, laser short, and powerful enough, you can get this radiation in your lab. Now, the spectrum has this kind of plateau in the cutoff. The cutoff frequency depends on the ionization potential of the medium that we're using and on the ponderomotive energy, which is basically the acceleration of the electron in the continuum while it travels, driven by the external electric field. And well, okay, one is interested in having a broad bandwidth here, covering with such harmonics. Now, this is well established. It got like this, let's say, approach for generating X-to-V pulses. Got the Nobel Prize in 2023 to Anne Lullier, Pierre Agostini, and Ferenc Krauts. And it's more than 20 years that people do this kind of source, X-to-V source. What was the idea that we brought in some years ago? The idea was to combine basically the microfluidic capabilities that we have in our institute, in which there are several groups working on doing microfluidics devices with femtosecond laser micromachining, and combine these with the capabilities of generating high-order harmonics that we have in my group. And so the idea is basically that you can get the same as the electric waveguide. In the X-to-V, it means to have hollow waveguide. And then with the femtosecond laser micromachining technique, you can create platforms for guiding your X-to-V light. This was the idea that we introduced, I think it was like 8 years ago or something, and we started developing. Just a couple of words on the micromachining technique. This is performed mostly in collaboration with Rebecca Martinez-Vázquez and the group of Roberto Zellame, but in our institute we have other people working on the same topic, also in different platforms. And basically what you do is that you take fused silica, you can irradiate with a femtosecond laser. You can do a 3D pattern inside your fused silica as you wish. And this gives rise to modification in the material. Then you can make a chemical etching, which is hydrolytic solution, and this will create basically empty channels into the fused silica. And then you can use those channels. You can couple the light, you can put gas inside, you can create a structure, making your light interacting with the gas. And I mean, like the first idea was really like, let's try it. And then we find out it can be really effective for nonlinear optics and harmonic generation. So this was the first, let's say, like the first results we published around 5 years ago. So this was the first idea, like let's make basically a channel in which we inject some gas, and then we couple our infrared laser driving the high-order harmonic generation process. And then what we get is the X-to-V pulses generated by high-order harmonics. And well, we just tried to do this. This is like the scheme, how it is, like with the gas inlets that you can easily do with femtosecond laser machining, and this is a calculation of the gas density that you get performed with the console finite element simulation. And here you can see that basically what happened is that if you inject the gas here, you get like basically a pressure which is kind of homogeneous along the channel, and depends on the vacuum pressure that we can measure accurately. And now what happened when you generate harmonics in this device? Well, we compared with our standard process. So like the usual way we were generating harmonics it was with a pulse valve. And then we compared this in the optimized situation with a microfluidic device. And this is what we got. The blue spectra is with the microfluidic device within the chip, and the red one is with the whole pulse valve. Please note that the red one is multiplied by a factor of 10. So what we got at first, it was like we got an improvement of the yield of an order of magnitude, but also we changed quite a lot the structure of our spectrum, and we were able to see an extended cutoff. So we extended like the bandwidth of our XUV pulse. So this was really promising and we were very happy. But of course, this is not a quantitative comparison because like the generation is extremely different. We can get an information on the gas density here with calculation. We don't have any information on the gas density here. The interaction is very different, and as in all nonlinear processes, the phase matching is extremely different, and in harmonics, phase matching is extremely important. So the idea since then was, let's try to do a quantitative assessment of this approach. And this is what we did with this publication. Here you can see again a spectrum, a order harmonic spectrum generated in the chip. This time we measured the photon flux. And here you can see that the red dot is the photon flux. I mean, the number here depends. It's meaningful for people that are familiar, but here you can get a feeling. Basically, the blue and red curves, it's our results in argon and neon. Is the same result. And helium is the same results shown here. And all the other dots is all the other setups for a order harmonic generation. And here you can see that basically around in this spectral region where we generate with argon, we are basically at the same level as state of the art. And then here we are one order of magnitude below. But I mean, we have a good reason here because we are limited by the pumping efficiency of our, let's say, generation chamber. Everything needs to be done in vacuum, and the pumping system was limiting our gas density. It was not the chip itself. So this was very promising results. It means that quantitatively this technique is really promising, comparable with the other, even like perspective of getting much more yield. Another now what I will show you now is that like from this starting point, what we did in the last 3-4 years, well 3 years. So how we developed this approach? Since we demonstrated it's promising, now we started developing it in a way, in different ways, studying the process itself and trying new approaches for really being able to do like an XUV source in a chip for experiments. Okay. So first, let's try to manipulate the phase matching. How can you do that? In order harmonics, you can do that in different ways. One of these is to change the density of the gas, which is tricky. It has been already demonstrated by a group of Pascal Saliere at COI in Paris years ago, doing with different pulse nozzles. And we wanted to do this within the chip. And for doing that, what Rebecca had to do is to design basically some nozzles and the different design of the chip in such a way that we were able to confine the gas. So we don't have any more gas density, which is basically like homogeneous along the channel. This time we have nozzles confining the gas density here. You can see these are console calculation reproducing the experimental setup. And where basically you have yellow and red, you can get like high density and generation of the harmonics. While where you have blue and green, you don't have gas density enough to generate harmonics. And this is what we got in this configuration with these two different chips. So one is the black spectrum and the red spectrum. Which is the difference? Well, you can see that the spectral extension is extremely different. This means that you are basically manipulating the phase matching with this approach, and this was nice. Now, from this point of view, one needs to have a very advanced calculation of the high-order harmonics generated into the chip, depending on the propagation of the infrared, propagation of the XUV in the plasma generated by the infrared, and also like the gas density taken into account in a way that to be able to reverse engineer and design a specific chip to get a specific phase matching. But this is in principle feasible. For this, we are collaborating with our long-term collaborator Valer Tosa in Cluj, who is doing calculation of propagation of high-order harmonics and generation, 3D propagation. So, I mean, this is work in progress. Then another point is how to extend the cutoff. I mean, the measurement that I showed you, like the spectrum is up to 150 eV. This is already quite interesting. But I mean, when we are interested to go for molecular physics to the water window to get to 300 eV, to 400 eV. And one way is to use longer wavelength driving lasers, because the cutoff depends on the driving wavelength, and it's actually like I mean, if one drives the harmonics with an OPA, for instance, around 1.5 micron, then one can get an extended cutoff. Now, I don't get into detail. If you're interested, we can discuss later. But what we did, it was to drive, like, to build an OPA at 1.5 micron with high intensity, like 1 millijoule, and short pulses, 25 femtosecond, and we coupled into the chip. And here you can see basically the spectrum that we get. We use metallic filter in order to see edges. And here you can see basically in of the harmonic spectrum generated with this, like, this one is the Cornell filter, this one is the Palladium filter, and you can see basically very clearly the carbon edge, because you have carbon contamination on your optics, which means that we have a very extended spectrum. This is really nice. Now, this source is now coupled to XUV beamline for transient absorption spectroscopy measurement, both in gas samples and in materials. And for materials, we have now both transmission geometry and reflection geometry, and we also have a cryostat in order to do measurement with temperature dependence. This beamline is available, let's say, for doing this transient absorption experiment coupled to the XUV source, and we are starting doing experiment. I'm not getting into the results of the experiment. I'm showing you, in the time that I have left, a few more perspective of direction of development for the chip, for the XUV, for the XUV source in the chip. One is the manipulation of the spatial properties of the XUV beams. This is something which is really not topic in high-order harmonic generation now, how to do structured light and how to design experiment with structured light. This is like something that is now very timely. And so we wanted, of course, to be like to propose an approach with our chip. And what we did, I mean, this is like a summary of application and different kind of approaches for generating for manipulating spatial properties. So what we tried to do, it was to generate vector beams in the chip. How you do that? Well, it's very easy, like to do it in the infrared. You just buy one of those zero-order vortex plates from Torlabs. You put it in your infrared field, and you get basically a modulation of your polarization. What you get is that you get a donut beam, basically, like the intensity distributed as a donut, and then you have, depending on the configuration, you have polarization, which depends on the spatial where are you, like on the spatial properties of the beam, basically. So here you can see the point that you can, like so this is the driving field, the infrared, and then here you have like the infrared beam. This is incoming beam after with the wavelet. And then you can couple into the chip and it gets out as it was at the beginning. And well, okay, but this is the infrared. What we want to see is if this infrared beam generate vector beam in the XUV. And for doing that, basically, you have to analyze your XUV spectra generated by the vector beam in different. And at first, with the spectrometer, what we got was that, okay, if you look at the spatial shape of your harmonics, you can see that you have harmonics in a donut shape. So the intensity is indeed the one of a vector beam. But is this true for the polarization? Well, we checked that. We have a polarimeter in our XUV spectrometer. And so what we can do is that we can basically assess the polarization state on different places along our beam, harmonic beam. So we can look at the top and at the side, and you can see that they have orthogonally polarized direction. And so you can turn your polarimeter, and what you expect is that you have the change in intensity of the transmission, and those two intensities should be out of phase. And this is kind of what we see. Indeed, this is not very clean. So at the moment, we are working on, let's say, reassessing these measurements to have better signal to noise. But in principle, we can say that, yes, we can generate vector beams in the XUV in the chip, which is interesting for several experiments. For instance, imaging that one can do in a Jordan harmonic spectroscopy. Then, another possibility. I mean, one other things that we did some time ago, it was to use beams of different colors. So combination of complex electric field, combining maybe like the fundamental and the second harmonics in order to generate the harmonics. For doing that, what do you expect? Well, the harmonic generation process depends on the shape of the electric field, not on the intensity. So if you combine two different colors and maybe you change the phase, what you do is that you basically are manipulating your electric field. And the electric field is manipulating the trajectory of your electrons. So you are basically manipulating intrinsically like the harmonic generation process. And this can be used for a Jordan harmonic spectroscopy. So for understanding from your spectrum the characteristics of the generating medium. So this time in your chip, you can put a molecule instead of an atom. And what you can do is that you use a complex electric field to generate the harmonics in this molecule. And then you acquire the spectrum and you extract information on the molecule. And you may extract information, like that's the same question I asked to Jerome. I mean, it's like you can extract some information, fundamental information on the ultrafast dynamics of the molecule and of different processes happen. And yeah, these are two setups, like basically like combining the fundamental and the second harmonics, or combining the fundamental with the third harmonics that one can use, for instance, in addressing like the interaction with chiral molecules. And then one has such complex, let's say, electron trajectories that are able to probe the chirality. And for now, I can only show that if you use two color beams, then you break the symmetry in the system and you generate different spectra, not only containing both harmonics, but also even harmonics. And then, I mean, the next step will be here. This is just argon, but then if you put a molecule here, we can start looking at this. We're doing this in collaboration with Emanuele Coccia from Università di Trieste. He designed, let's say, the interaction, and we are doing the experiment. Another let's say, development. Of course, when you're coupling a laser into a fiber, you can have like your laser is coupled to the modes of the fiber, right? So in general, when we couple to hollow waveguides, we usually couple to the fundamental mode. But I mean, our chip is 8 millimeter long, so the losses are not enough to exclude that we have higher modes. And so we can have the interplay, the interference basically in the intensity of the different modes that are excited in the chip. And what happened there is that we may have a very complex intensity pattern in the infrared, which is the one triggering the harmonic generation process. So this is another knob that we can play with and that we have to understand in order for this to be a reliable technology. And so what we did here is like, okay, for instance, like we can calculate the multi-mode excitation. These are, for instance, like 4 modes that we can excite. And then we have mode beating. This is all calculation along the fiber, like along the chip. And then, this is an experiment. This is the experimental result. So here, what we're doing is that we change the coupling by changing the focal spot. So you are just changing the place, like the position of your focus with respect to the entrance of your fiber, and so you are coupling differently to the various modes. And then you look at the harmonic generated, and you can see that depending on the focal position, you really have different spectra. And then of course this needs to have advanced calculation to understand, because you are changing several parameters while you are changing the position of the focus. But indeed, like those calculation needs to take into account the excitation of higher order modes in order to reproduce the experiment. So these are calculation by Valerio Tosa with the contribution of different modes in different positions, and we are now in the process of reproducing this map with the role of the different modes. Okay, I'm in time. Another development, another direction in XUV experiment. You are generating your XUV with an infrared beam, and the infrared beam is really like it's strong. And then you have the infrared overlapped with the XUV. And for most of the experiment, you don't want the infrared, because the infrared is going to basically interact with your sample at the same time as the XUV. So it's making everything messy. So you want to get rid of it. How do you do that? Usually with metallic filters. Metallic filters have a very good rejection, but of course they have bandwidth. Also, they need to be thin, because the XUV is weak, and so they damage very quickly, and they are very expensive. So what we thought is, why don't we try to guide the infrared away? So we did like this filtering structure. We have a chip for generating the harmonics, and then we have a chip for guiding the infrared away and trying to guide the XUV toward the experiment. And yeah, and that's basically the design and how it looks at the microscope. Of course, this is really huge. The radius is very small. This is how it looks at the microscope. This is how it looks, let's say, the interaction with the laser. And this is the results that we get. Here you can get that you have basically like the infrared, and in the main channel transmitting XUV, we have basically like 1% of the infrared. And here you can see transmission. Of course, the rejection is not comparable as metallic filter, but what we are testing now is this is good enough for our experiments, because anyway the infrared is then diverging and is not refocused on the sample. So maybe this 1% is variable, or at least then you can put your metallic filter and you don't damage it. So that's quite interesting. Yeah, okay. And I mentioned, I don't have a slide, but I mentioned that we are trying also to build sample delivery with the chip and interferometry. Like we are trying, Rebecca is working hard to try to guide the XUV. And for this, we have also collaboration with Fermi, the free electron laser in Trieste. And also to realize some kind of, let's say, beam splitter or like interferometer within the chip. And if we manage to have all these, let's say, pieces in place, our dream would be to make a very compact platform for higher harmonic generation. So yeah, that's from perspective. Well, what we did in the last, I would say, like 8 years or so, it was to develop this platform based on femtosecond laser micromachining and higher harmonic generation combined. I would like to stress that these are two research topics that like you need like very specialized people to work on both ends in order to be able to combine them. It's not as simple as buying a chip and placing that into the chamber. But then, the perspective is that we may be able, let's say, to go from, well, okay, this is a bit ambitious and probably not like very far-fetched, but from large-scale facility to really palm-top integrated photonics. Recently, all these experimental development that I've shown have been implemented within 2 research infrastructure funded by the like the PNRR, the recovery funds from the Italian government, and these are infrastructure open for access. So both the NSFLDI and the IFOX platform are open for collaboration. In our case, this one is on materials, this one is on molecules, and more quantum effects. But I mean, like, if you're interested in collaboration, like, that's open. And finally, I'd like to show the people that really like did all this development. In particular, Rebecca for the chip platform, and Anna here for all the up-to-second technology within the chip. And then Kamal, PhD student working on that, Stavrul as well, PhD student working on the chip, and other people from the lab that I mean, contributed somehow. And with this, I thank you for your attention.
Thank you very much. Nice presentation. So, questions for Caterina, please.
Yes. I mean, it's like in a waveguide. I mean, like if you bend the waveguide, you have losses, but you also guide. I mean, depending on the radius, like you may have major losses, but you can also like you can guide the portion of, and that's the same basically. So the guiding is similar. Of course, it's a hollow channel because I mean, like but it works the same up to some extent. If the radius is not too much, the losses are not so much, so that portion of the infrared goes away, let's say. But I mean, it's basically it's like leaky guiding in that direction, basically. Yeah. And then this is why also there is 1% that goes straight, of course, because like you cannot avoid it. And you play with the dimension of the two channel as well. For the X2V, of course, you need a smaller channel. The X2V so far is not guided. This is something that Rebecca is working on right now. But you can make a small channel and like you cut. And then if you look at the picture, there is interferences between the two infrared, of course, because like that's what you expect, because you also have some in between the two, somehow, the losses. That's the point. In order to be able to guide the problem is not the size of the channel, because the femtosecond laser micromachining, like they can go to like few microns. So I mean, that's fine. But then there are those ripples that are intrinsic of the, and they like basically what Rebecca is doing is she's trying to make and order like tricks, let's say, to reduce this roughness. And then what she's doing is that she is basically trying this, but instead of doing that in the lab, she's doing that at the perimeter electron laser. Because of course, having a powerful source enable you to assess the losses much better with our few photos of their work source. But yeah, I mean, like that's the thing is, indeed, the roughness is the main problem for losses. It's what is preventing for guiding, and there are techniques to address this roughness and to try to minimize it. Yes. Okay. This was something that we did for fun, in the sense that we didn't ever use it for generating algorithms. But indeed, the manipulation of the diameter of the fiber is another way to manipulate the phase matching, and indeed we can do it. Now, the main point is about the reverse engineering, to know what you're doing. Actually, yes, you're right that you did some of the seminal experiments on this, let's say, phase matching manipulation with multiple. But at that time, I mean, nobody knows when to start, right? So, like that was the starting of. I'm sorry that I didn't mention that. But yeah, I mean, it's like there are all those ingredients that are known, so you can modulate the intensity of your driving field by changing the diameter of the chip. Then you can change like the density of the gas. You can combine the two. The point is to know what you're doing, and for that you need really advanced calculation of a order harmonic generation in a 3D way, which is not so accessible, particularly because theoreticians, I mean, the one we're collaborating with, they are very good in doing that, but they are triggered by, like, they have their interest. For instance, now they are all on the multiple modes, and they don't follow us with this. Like, we have to push them to. But yes, I mean, we are going there. No, 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 no. Okay, so we try. We can try. We are not going to try these. This was just for fun to see the capabilities. We are going to do it in a simpler way. But yes, we are going to. Well, I would say that the theory is demanding, but also the experiment is demanding. Recently, we made some adjustments with the pointing stabilization that made the approach much more robust. Before, it has been painful for a few years, like whenever you have to assess a different chip and change it, like it was quite complex. Now it's much more easy, as usual, when you develop the technique. Yes,
Many like that. So that story on
yes. Uh, yes. And we have to be very active. So this is something that we can do. We're thinking about doing. Again, it's like, well, designing is like such a way. But we even have a plan. We are discussing. One thing that one would like to do is also optics, or maybe diagnostics of 5G. And like electrodes, for instance, it would be nice to have actuators, and it would be nice to have electrodes. So it is something that we are thinking of. And from this point of view, okay, like we are very happy to share ideas and have collaboration. If there are people interested, so.
very good. Thank you. Thank you very much.